In the early stages of development, our lunar economy will be small, consuming less than 100 megawatts of power. But it will be human-oriented, so it will need to remain powered throughout the long lunar night to keep spaces habitable to humans. So importing continuous energy sources from Earth, like nuclear reactors or fuel cells, makes sense at first. But to build something like a Stanford tourist station, our lunar economy will need to be massive, consuming gigawatts worth of power. But it should also be almost entirely machine-oriented, and there is no reason our machines need to run at night. So what we need to develop are scalable solar power energy solutions, and they'll be much more scalable if they are made on the moon, out of the moon. I'll admit this topic isn't as exciting as strip mining the moon and mass drivers and O'Neill cylinders, but generating gigawatts of power is essential to powering all those things that are interesting, so this topic needs to be addressed. We have two options: photovoltaic solar cells or solar thermal solutions. At first, it seems like the thermal solution is the best, since it could be done without any imports, and it can achieve much higher efficiencies. Solar thermal solutions can have high-end efficiencies of over 50%, with a typical low end of about 20%, while crystalline silicon solar cells like the ones on your roof are usually around 20 to 30%. However, we have chosen to use amorphous silicon cells, like those on old calculators, for many reasons, including radiation tolerance and production cost, as discussed in the previous video, but these kind would likely max out around 12%. In other words, some of the worst solar solutions have efficiencies as good as some of the best solar cell designs, better than the designs we would be making on the moon. Not only does thermal have higher efficiencies, but we're also operating in an environment with abundant thermal energy. The lunar environment lends itself to solar thermal, as without an atmosphere there is no convection, so we can achieve extremely hot temperatures quite easily. Even the lunar daytime temp is naturally hot, peaking at about 121 degrees Celsius or 250 degrees Fahrenheit at the equator. But photovoltaic solar cells beat the shit out of solar thermal every time because they require less mass per square meter per watt, meaning they require less refining, less manufacturing, lower cost deployment, less energy invested for the same energy generated, and I have graphs to prove it. In the previous video on solar cells, we listed all the options we had available and then approached a final design by narrowing them down based on, well, lots of things. Go watch the video. For this video, we'll do the same. We'll try to approach the best solar thermal system design as a way to steelman the solar thermal argument before finally comparing it to solar cells. To generate electricity from thermal energy, we use a generator, and to run a generator on thermal energy, we use a heat engine, and to run a heat engine, we need a cold side and a hot side. The greater the difference between the two, the more efficient the engine is. To generate a hot side, we concentrate solar energy. To concentrate solar energy, we use reflectors, and to create a cold side, we use a radiator. So those are the four basic components: reflectors, heat engine, generator, radiator. The generator is easy. It can be made of iron and aluminum and follow the same designs we use here on Earth. For the reflectors, we can make reflective surfaces on the moon using deposition. Aluminum works great and is very abundant on the moon. Even if it wasn't, the amount of aluminum required is very small, since we only need to deposit a layer 400 nanometers thick, meaning about 30 grams of aluminum would be enough to coat a surface area of 100 square meters, or about 300 kilograms per square kilometer. Schleppy, Gibbons, and friends were able to make aluminum mirrors from regolith simulant by depositing aluminum onto a regolith glass substrate, and were able to achieve up to 90% reflectivity. While we don't need much aluminum for the thin reflective surface, we will need lots of that which the aluminum is deposited onto, the hard structure of the mirror itself, the substrate. To achieve gigawatt scales, we are looking at covering square kilometers worth of area in mirrors. Two options are cheap enough to make sense. Either we can melt regolith into a rough obsidian-like glass, as was done in this study, or we can simply make aluminum foil. Both have advantages and disadvantages. If we deposit the aluminum onto a glass, the surface topology will have a big impact on reflectivity, so the substrates will need to be polished using an abrasive. The authors of the study were able to do this and still achieve 90% reflectivity using an automatic polishing system. Then we need to deposit the aluminum onto this clean surface using deposition. If we instead made aluminum foil, we probably wouldn't need to polish or use deposition, but we would need much more refined aluminum. If the foil is about the same thickness as your typical kitchen foil, then we need about 44 metric tons of foil per square kilometer. Refining and depositing and polishing all consume energy. So ultimately, which is best will come down to the cost of refining pure aluminum from regolith, which will depend on the method used, which is discussed in our video on metallurgy. As for the actual architecture of the reflectors themselves, we have multiple options. We can use dishes or parabolic troughs or linear arrays. Each one has certain advantages and disadvantages. Some use more material, but others are easier to deploy or are easier to set up with a tracking system, while others may use less material but might have to be assembled on site from individual components rather than just set out. It's hard to know exactly which is best, and context matters. For example, tracking dishes may be better at higher latitudes, while non-tracking linear arrays might be better near the equator, but since they all have the same fundamental principles, we'll just count those. For the animation, I'm going to show a linear array, but understand this is just one option. We'll also assume a non-tracking system at the equator for simplicity's sake. It would be a different story if we could make the reflectors tracking much easier than the solar cells. That would definitely be an advantage, but this really isn't the case, as both could be made tracking for a similar mass expense, and in both cases, tracking might not be worth it, or can be thought of as a future optimization. In the radiator, we need a fluid that has high thermal conductivity to carry energy away from the engine, creating a cold end. It can also be used in some designs, like that of the linear array, to carry heat from the receiver to the hot end of the engine, but its primary use will be in the radiator. Sodium-potassium alloy, or NaC, is probably our best candidate. While we don't have many liquids on the moon, we have a good amount of sodium and potassium, which when combined create a eutectic mixture, which means the melting point is lowered more than that of the constituent elements it's made of. Both constituent elements, sodium and potassium, are solid at room temperature and have high melting temps of 97 and 63 degrees Celsius respectively. But when combined to create NaC, we get a melting temp of negative 12.6 degrees. So it is a liquid at room temperature, but it also has a very high boiling point of 785 degrees. So it can remain a liquid across a wide range of temperatures. Also, for the rest of the video, when I say degrees, I'm talking about Celsius. More importantly, NaC is a metallic liquid and as such has very high thermal conductivity, which is why it's become an increasingly popular coolant in nuclear reactors and high-temp gas turbines, and even this CPU cooler. It's not hard to make. We have relatively large amounts of sodium and potassium on the moon, and there's no wet atmosphere for it to react with. For the actual heat pipes themselves, aluminum has higher thermal conductivity than iron or steel, so I considered that at first, but I think NaC reacts with it. I haven't been able to confirm this directly, but of all the NaC heat pipe compatible material data sheets I read, none listed aluminum as compatible with NaC, despite listing it elsewhere. For NaC, they all listed stainless steel, although exactly what type wasn't specified. Emissivity is an especially important property for the radiator, and cold rolled steel can reach good emissivity levels of up to 0.8. For the all-important heat engine, we really have two options: turbines or Stirling engines. Both are relatively simple mechanisms at their core, but increase in complexity as we increase their efficiency. Both use standard materials, nothing exotic, and both can be made big or small from machined parts, so they have similar manufacturing complexity and scalability. But Stirling engines are the better option because they can run hotter. A Stirling engine's hot end upper limit is set by the melting temp of the engine material itself, which can be made quite thick and thermally tolerant. If we assume this is steel, the sublimation temperature of iron or steel in a lunar vacuum is around 1100 degrees, but it becomes malleable around 850 degrees. So to be safe, let's set an upper limit of just 800 degrees, a temperature we know we can work with because we've actually already built Stirling engines that run this hot. A turbine's hot end upper limit is set by the melting temp of the turbine's blades, which have to be thin, and therefore aren't as thermally tolerant unless a cooling gas is pumped through them, as is done in some high temperature combustion gas turbines. But this adds a ton of complexity, as we're now talking about adding an entire new gas cooling system, which also has to be manufactured and integrated into the turbine and blades, which would require them to be redesigned in a way that would increase their manufacturing complexity, as they'd need to be hollow rather than just being solid steel machined into simple shapes. Without this extra complex cooling system, normal steam turbines typically have an upper heat limit of about 650 degrees. But why is hotter better? In both cases, our engine efficiency is determined by the temperature difference between the hot and cold ends. So what if Stirling engines can run 150 degrees hotter than turbines? Just make the cold end 150 degrees colder to compensate. Well, the temperature of our radiator will be how cold the cold end of our system is, and the radiator cannot be colder than the ambient temperature around it. Ambient in this sense is a little weird because we are in a vacuum, but this vacuum is full of energy from the sun and reflected radiation from the lunar surface, mostly infrared. So while there is not a warm atmospheric medium, anything in this vacuum will absorb all this energy until it heats up to 120 degrees Celsius. So the radiator, and thus the cold end of our heat engine, cannot be colder than this ambient 120 degree environment. And as such, all that free thermal energy, so often heralded as the reason to use thermal systems on the moon, is, as we'll see, actually one of their biggest downfalls, because you need cold just as much as you need heat. One idea that my half-baked brain coughed up was to shield the radiator from the sun by putting it under the reflectors, which is how spacecraft radiators often run cooler than 120 degrees Celsius. But unlike spacecraft, we are unable to radiate into endless empty space. We'll have to radiate into the moon's surface below and the reflectors above, both of which will re-emit that energy as infrared radiation. But even if we could get our radiator temp below 100, we might not want to. This is a bit counterintuitive, but we actually want to run the radiator hot because the hotter it runs, the smaller it can be. On Earth, it's quite cheap to cool stuff down because we have rivers and an atmosphere, so radiators on power plants don't need to be that big. This is why power plants use big retention ponds. Maybe you can even consider the ponds a part of the radiator system that we get for free from Mother Nature. On the moon, we have no Mother Nature, no rivers or ponds, just hard vacuum and heat. So the radiator has to be massive to compensate for the lack of convection. How big it will need to be can be described through the Stefan-Boltzmann equation. To find the surface area, we can rearrange the equation like this. Notice that surface area is inversely proportional to the fourth power of temperature. So as the temperature increases, the necessary surface area required to emit the same amount of power decreases drastically. If the temperature of a radiator doubles, the radiator can be 16 times smaller while still emitting the same amount of power. Stirling engines having a higher hot end capacity means we can run the radiator hotter and achieve the same level of efficiency, which means at any given level of efficiency, we can have a smaller radiator as compared to turbines. So that's our solar thermal system. Aluminum iron generators powered by Stirling engines, heated up using aluminum reflectors, and cooled using stainless steel NAC radiators. How does it stack up against our thin film amorphous silicon cells? To compare the two, we need to measure using energy returned on energy invested, as this allows us to evaluate the viability of things outside the bounds of a price-setting market. In a consumer market, if something is 2 times the quality, but costs 10 times more money, is it worth it? Most people would say no, it is a bad deal. Similarly, if something generates 2 times as much energy as an alternative, but costs 10 times as much to produce, it is also a bad deal. For everything we have to make, we have to refine mass. We have to turn regolith into materials. For every kilogram of refined mass, we have to spend energy. And while it's impossible to know exactly how much energy will be required to make every component of each system from start to finish without actual production and testing, a good estimate is how much mass is required per watt produced. So, to compare our solar Stirling to our solar cells, we will approximate each one's mass per megawatt at different efficiencies. We will not be counting power transmission lines because they will be very similar in both systems and can really be considered a separate system altogether, the grid. So counting it just overcomplicates things without really changing the outcome. Although in the case of the solar cells, I have included the mass of the small wires that are a necessary part of the cell contacting the top and bottom contacts to carry energy out of the cell and into the grid by adding 20% of the bottom aluminum contact's mass. In the solar cell video, we calculated the thickness and materials of each layer, but we didn't go so far as adding everything up into a total grams per meter amount. But assuming we go with the cell design that uses 20 micron cover glass, a fluoride doped 10 oxide transparent conductive film, 400 nanometers of amorphous silicon, and an aluminum bottom contact with wires, we get a total mass of 101.76 grams a square meter. As efficiency decreases, the amount of surface area required to generate 1 megawatt of electricity increases, meaning you need more solar cells and therefore more mass to achieve the same result at lower efficiencies. So if higher efficiencies mean less mass, then higher efficiencies are better, right? Well, yeah, in the case of solar cells, but they don't have a radiator. In the case of our solar thermal system, the radiator size has an inverse relationship with efficiency. Radiator size is determined by working temperature. Hotter is smaller, smaller is less steel and knack, but hotter is also less efficient. So to calculate the mass per megawatt of the solar thermal system, we will set a hot end temperature of 800 degrees, and then we have to calculate the basic Carnot efficiencies of different cold end temperatures. These will determine radiator size as well as efficiency. Once we have ideal Carnot efficiency, we can adjust it for realism by accounting for the sun's angle and system losses to approximate expected real efficiencies. Once we have these, we can find the reflective surface area required to generate 1 megawatt of electricity at these efficiencies, which determines the amount of reflective mass we need. Then we can go back to the temperatures and determine the surface area required to radiate each temp, and then we can estimate the length of pipe required to do this, and from that, the amount of steel needed for the radiator. Then we can find the power density of modern Stirling generators to estimate the mass of the Stirling engines and generators required for 1 megawatt. And then we can add it all up and graph it to see how it compares to the solar cells. So yeah, we have our work cut out for us. Or I guess just I do. You get to exist in the future watching this video after I've already calculated everything. According to my calculations, the basic Carnot ideal efficiency of the different cold ends from 120 to 800 would look like this. But this isn't the full picture. We need to measure from the surface area of the sun being reflected into the hot end of the Stirling engine, not just the engine efficiency itself. The reflectors are just as much a part of this system as the engine and generator. The average solar energy received on the moon's surface is approximately 63% of the maximum possible solar energy, because the amount of solar energy received depends on the angle between the sun's rays and the surface. To find this, we divide the diameter of the moon by half the circumference and get 0.63 or 63%. The sun's full power in space, unfiltered by an atmosphere, is about 1,360 watts per square meter. 63% of this is 856.8 watts per square meter, which is the average our reflectors will reflect onto the receiver. Assuming our reflectors are 90% efficient, we lose another 10% and are left with 771.7 watts a square meter, just 57% of the sun's full power on average. So we've lost, on average, 43% of our energy by the time it even hits the hot end receiver of the Stirling engine. Applying this 57% to our table, we get a much more realistic picture of efficiencies. Then we need to account for the generator losses, which are typically only about 5%. In reality, we usually achieve between 50 to 70% of the actual ideal Carnot efficiency due to mechanical losses and other inefficiencies, but we can be optimistic and say we'll achieve 80% of the Carnot ideal, so we'll add a column for that too. Now that we have our realistic efficiencies, we can calculate the amount of reflective surface area needed at each of these to generate 1 megawatt of electricity. For the actual reflector mass, we can either do the glass panels or aluminum foil, and the difference really depends on the cost of refining that aluminum. But since we don't know what that will be, we'll just go with the foil since it has less mass overall. Even if that mass comes at a greater cost, we aren't counting it, so the foil will play more favorably here. Typical kitchen foil is about 0.016 millimeters thick. If made of aluminum, we need 43.2 grams per square meter. So we can add the surface area of reflectors required for 1 megawatt at each efficiency, which will determine the reflector's mass per efficiency. Finally, we need to calculate the surface area of the radiator at these different temperature efficiencies. We can do this using the rearranged Stefan-Boltzmann equation. This table shows the surface area required to radiate different temperatures of a 1 megawatt system using cold rolled steel with an emissivity of 0.8. Then we can calculate the total length of pipe required per efficiency by calculating the lateral side of a cylinder, but to do this we need to define our pipe diameter. Because of the square cubed law and the fact that larger pipes require thicker walls, we are better off using smaller pipes. But smaller pipes have higher pressures and thinner walls have lower thermal tolerances. Instead of doing a deep dive analysis, I just decided to see what's commonly used in radiators today, which appears to typically be pipes with a diameter of about 2 centimeters. With this info, we can calculate the total length of the needed pipes. 2 centimeter stainless steel pipes usually have walls that are 2 millimeters thick, so using this we can add another column, the amount of steel required at each efficiency. To estimate the mass of the Stirling engine and power generator, we can average the power density of modern existing Stirling generator systems. I was able to find this review of all commercially available Stirling power systems in which the authors graciously noted the mass of the power systems for those that were known. This table was really a treasure trove to stumble upon, and it even included info for systems no longer on the market. I averaged all of them that had a noted mass and got about 25 watts a kilogram, which means for 1 megawatt of Stirling generated electricity, we'd need 40,000 kilograms or 44 metric tons of mass to create the Stirling generator system. Adding up all of the masses, we can graph the system's mass per efficiency, which is very interesting. Notice that it is a parabola decreasing in mass as we decrease in efficiency, but only to a point, around 8%, where it then begins to increase in mass again. The reason we decrease in mass with efficiency is because as we get less efficient by running our radiator hotter, the size of the radiator decreases by the power of 4, while surface area only increases exponentially. But then what is happening at 8%? Why does the mass begin to increase again? Well, this increase in mass is not from the radiator, but rather from the required reflector area. At this point, the amount of reflector surface required begins to exponentially increase, while the radiator cannot run much hotter as it approaches 800 degrees. Now we can see how it stacks up to solar by adding in our solar graph at these same efficiencies. And oof, yeah, it doesn't look good for solar thermal. Even without reflectors and radiators, the engine and generator mass alone is enough to completely swamp it, and this is mostly because it had such a low energy density. But what if we had a way to generate electricity using thermal energy that had a much higher power density, so less mass per watt, and a much higher working temperature, so a much smaller radiator would be needed. Magneto-hydrodynamic generators are a possible saving grace of solar thermal, as they do exactly this. Magneto-hydrodynamic power generation is a mouthful, so we'll just call them MHD going forward. MHD generators work by blasting a conductive fluid, typically an ionized gas or plasma heated to very high temperatures, through a magnetic field. When it moves through the magnetic field, the motion of charged particles in the fluid induces an electric current, which is captured by electrodes positioned along the channel walls. While a plasma is generally used, we can also use a liquid metal, and as we already discussed, we have a lot of knack. The major advantage of these systems is their efficiency is determined by their temperature, not the temperature difference between the hot and cold end. So their efficiency is not determined by the size of the radiator, which means they can achieve very high energy densities, watts per kilogram. They do still need a radiator, but only to keep the thing from melting itself, which means our radiator could run at like 700 or 800 degrees or more, so it could be quite small. Their high power density and lack of moving parts created a lot of interest in them for spacecraft in the 1960s and 70s, so most of the research on them is actually from NASA, and I was able to find one NAC MHD generator built by NASA in the 70s, which was able to achieve a net efficiency of 26%. But MHD generators for spacecraft kind of fell out of favor at around the same time as nuclear reactors because solar cells increased in efficiency and spacecraft in general became smaller and lighter. Nuclear reactors and MHD generators were simply overkill and really only made sense for massive spacecraft on long-term deep space missions. However, over the years, MHDs have maintained sort of a cult following, and there has been some interest in them, especially for manned Mars missions. For this very purpose, in 2006, these cool guys published this awesome paper which does a detailed analysis of an MHD system, and found a peak power density of 600 watts per kilogram at 30% efficiency. Because efficiency is determined directly by the heat and not the heat gradient, we don't need to count different efficiencies as a measure of system mass. What I mean by that is, for the thermal system, the efficiency was determined by how cold the cold end was, so the more efficient it was, the more mass it had, the lower energy density, more kilograms per watt generated. But again, the magic of the MHD system is its efficiency is just determined by how much heat you can pump into it. No cold required. And with the 600 watt per kilogram 30% efficient MHD system modeled in this paper, we get a flat 1,666 kilograms for 1 megawatt, which puts the crossover at about 5%. So if the solar cells are less than 5% efficient, this MHD system is better, but over 5%, solar still wins. And I should note that like with solar thermal, we are actually being really easy on this MHD system, because this paper bases most of its mass calculations on typical values of components, which means Earth-made components. They are not restricting themselves to lunar-based materials. And if we consider complex systems that aren't restricted to lunar-based materials, then it opens up the door to nuclear reactors, so it kind of defeats the whole point of this scenario, which again is to find a cheap and scalable power solution made on the moon, out of the moon, for a gigawatt or even terawatt scale lunar industry. As always, I've published these data tables and graphs, and I'll link it in the description for all to access. Now, on the topic of power generation, the last thing I want to do is talk briefly about power transmission cables on the moon. Long distance cables are very, very heavy and bulky, so they're going to be right at the top of the list of things we'd want to manufacture in situ. Fortunately, they are quite simple, really just being a bundle of wires wrapped in insulation. There are many different varieties, materials, sizes, and configurations. We'll set all that aside and just talk about the basics: wires and insulation. As with most conductive things we've talked about on the moon, instead of copper, it makes sense to use aluminum, since we have basically no copper, but lots of aluminum. Aluminum is only about 60% as conductive as copper, but it's 3 times lighter, which allows for the use of larger diameters to compensate for this loss in conductivity, while still reducing the overall weight. It's also much more flexible than copper, has a higher strength to weight ratio, and is more corrosion resistant, which is why aluminum is the preferred material for high voltage, long distance power transmission lines even here on Earth, and aerospace applications. Wire creation is a well-established process, but the basic approach is to cast molten aluminum into long rods, which are then rolled to reduce their diameter and improve the crystalline structure. After this, they are cooled and then coiled. Once coiled, smaller gauge wires can then be created from these rods through the process of wire drawing, in which the rod is pulled through a series of progressively smaller dies, reducing the rod's diameter and increasing its length. So that's how we can make the wires. Quite simple. But what about the second part of power cables, the insulation? On Earth, we obviously wrap wires in an insulating material to protect people from being shocked for safety, but also to protect the wires themselves from the environment, namely water. On the moon, we can insulate the wires in areas trafficked by humans, but that's going to be a tiny percentage of the grid, which will mostly be distributed across vast swaths of uninhabited terrain. So preventing people from being shocked is not our top priority here. Since there is no water or atmosphere or flora or fauna, do we still need to insulate our power cables? Or could we just leave the electrodes exposed? Unfortunately, we do still need to insulate because when bare conductor materials are exposed to the lunar vacuum, the electrode surfaces will be altered due to charged particles and thermal stress, causing electrical breakdown of the system and enhanced field emissions, which is the loss of electrons and charged particles to the vacuum. These emissions would initiate micro or bulk discharges, which would result in system failure. We have no hydrocarbons on the moon, so we can't use rubber or plastic, and even if we did, rubber and plastic would off-gas in the lunar vacuum. So what can we use? Well, glass has been used as an insulator on power lines since the invention of the telegraph. We have no shortage of materials to make glass on the moon, and are likely to set up glass manufacturing lines for other reasons. To insulate wires in glass, we can use glass fibers. But mineral fibers are probably an even better alternative. Mineral fiber is basically an unrefined version of glass fiber with mostly the same properties and can be made directly from lunar regolith quite cheaply. When we melt lunar regolith, we get what is in essence lava, which is fundamentally molten volcanic glass like obsidian, which is principally molten glass that's full of impurities like iron, which can essentially be extruded through a spinneret to form what are basically thin fibers, which can then be used to wrap our wires, creating what is often a flexible mineral wool aluminum wire cable. And the company Moonfiber has predominantly been working on this since 2019. But wait, if mineral fiber derived from lunar regolith is an insulator, does that mean just regular lunar regolith is an insulator? And if so, why not just use that? Why not just bury the wires under a few centimeters of packed regolith? Well, that's exactly what Kirkichi and Chalupka tested in 1996, and it turns out, yeah, we basically can. Lunar regolith makes for a good insulator with a high resistivity of about 10 to the 12th power ohms a millimeter. But I've also seen that in many other studies, uncovered electrodes have been the primary method used to melt lunar regolith. So how could regolith be an insulator for electrodes in one study but be melted by electrodes in other studies? Well, really it comes down to the voltage. In electronics, electrical breakdown occurs when an insulator suddenly becomes a conductor and current flows through it. This happens when the electric field caused by an applied voltage exceeds the material's dielectric strength. Kirkichi and Chalupka found that the breakdown of lunar regolith occurred around 6 kilovolts, but dropped with successive tests. The authors attributed this drop due to static charges left in the regolith between testing rounds, as they only allowed 15 minutes between runs, which they believed was not enough to dissipate all the charges. As heat increases, conductivity decreases, and the resistance of the wire will create ambient heat around it. So we should bury the cables deep enough that they are in the region of highly compact regolith, which will increase thermal conductivity away from the cable, and also compact the backfill for the same reason, as well as for long-term physical stability. A relevant side note worth mentioning is that on the moon we have the option to bury cables in permanently shaded regions, which have very cold ambient temperatures. The Planetary Surface Technology Development Lab at Michigan Technological University simulated this by burying cables and using liquid nitrogen to simulate a permanently shaded region, and was able to achieve superconductivity. Since this approach is limited geographically, it isn't a universal solution, but it is a good option we have for certain applications, and I thought it was worth noting. So burying electrodes is the cheapest solution for obvious reasons, and makes sense for long distance power transmission. But in situations where we need to use cables above ground, say for transmitting power to a large vehicle, then we can go with the mineral fiber wrapped option. In both cases, we're using regolith as the insulator. So that's it. Just dig a shallow trench a few centimeters deep, lay down some electrodes, and then cover it and temper it to pack the regolith tight. Maybe poke in some little flags so you remember where it is, because remember kids, around 100 million people die excruciating deaths a year from accidentally digging up power lines and gas pipes in their backyards. So always call before you dig. Thank you guys so much for watching and engaging, and thank you to the patron and channel members whose support is absolutely invaluable in allowing me to do these kinds of deep dives. Without you guys, I wouldn't be able to justify the massive amount of time required to research in depth. So seriously, thank you.